Hi, I'm Ella Atkins.
Hi, I'm Jeremy Castagno.
We're going to be giving the next session that's called Rooftop Landings for Safe Urban Drone Operations. So just to set the stage, we all know that we're going to have a lot of unmanned aircraft and maybe urban air mobility platforms that are much larger flying around all the cities, George Jetson style for the large ones, Amazon Prime Air style for the small ones. So if something happens, ideally there'll be enough redundancy in the systems and enough intelligence in the onboard software to make sure that people and property are not damaged. On the other hand, if there's a densely populated urban environment like Manhattan, San Francisco, and many other urban centers, it may not be a good idea to deploy a parachute and fall wherever it was that the problem first happened, because that parachute could easily land on someone's head or the windshield of a car. So better than that is to look in advance using all of the GIS, Geographic Information System, building data, and other data sources that you have available to ask the question, if you have to land in the next seconds or couple of minutes, where should you go? If you really are in an open area, clearly a grassy or brown field, an empty parking lot where no one is because it's 2 a.m. and nobody really shops at 2 a.m. in a closed mall, those are great. If you're downtown during rush hour, you probably don't want to land anywhere on the street, anywhere on the sidewalk, or even in a city park. So what we're going to be talking about is how do you take advantage of infrastructure that hasn't been used in the past for things like aviation. That would be rooftops. Now obviously you don't want a rooftop to carry a manned aircraft when it was never designed to hold that much weight, because that would be a disaster, right? The whole structure fails, the things crash through the roof. But that's not what we're talking about. We're talking about the vehicles that have anywhere from a 1 to 5 pound payload that are much lighter even than you and I when we fly around, when they fly around and we walk around. So that's where we're going to talk about something a little different, which is how do you find rooftop landing sites and use them for emergency landing if you're a drone? So this is the agenda. Looks too much like a conference presentation. I won't spend that much time on it, but I'm going to start out the presentation leading you through kind of a background of what planes do, what UAS do, and then what is contingency management and how could we use that information to build better maps of landing sites than what we've had before. So the folks who organized this event said you have to put a bio first. So this is me. You can read the credentials there. I'm going to talk about aviation because this type of work really blends not only what people have studied in school and what they do in research or their job, but also their experiences in life. So I lived in San Diego and was in industry for a few years after I got my first set of degrees. And one of the first things I did was learn how to be a pilot. San Diego is a great place to learn to fly. You can fly 12 months a year. I'm in Michigan now. Not quite so true unless you really enjoy cold weather. And it was great, right? Busy airspace, lots of chatter on the voice-based air traffic control, and on weekends you get out in an airplane and get out of town. Once you're over the desert, it's like you're there and nobody else is around you. So it's spectacular. Now, once I got my license, few things happened that weren't quite so great that set me on a path of studying aviation safety and autonomy for flight. Within a year of getting my private pilot's license, 2 of the 3 main airplanes that I flew in crashed and people died. One nose down in Interstate 15, I believe it was. People were drunk and stole the plane and crashed it. The other one, the main Cessna 150, commuter, by the way, that I learned to fly in, had an engine failure near Borrego Springs, which is kind of the middle of the desert. And that one also crashed doing the impossible turn back to the airport. Turned out that second one hit a little closer to home, not only because I had flown it, but because when they did the forensic analysis, they found that the wrong parts had been used in the engine and that it would have failed sometime, maybe a little sooner when I had been flying it. Now, one of the things that always happens when you learn to fly is the flight instructor, your examiner says, hey, where would you land? Pretend your engine is out. They pull the throttle back to idle. Any of you pilots? Well, anyway, this happens. One of the things that they train you in is engine out landings. So imagine that you're over canyons and mountainous areas of Southern California. and they pull the throttle back to idle and say, pretend you have no engine, now land. I was always really bad at that because you have to time it right, you have to be aware of what's around you, you have to be aware of where the clear areas are, where the local runways are, and then you have to get there. Well, those math calculations are not very easy for a person who's already kind of panicked because their engine has failed. They're pretty easy for a computer, and it doesn't take AI to do that. The other thing that happened, so I actually had a happy situation. I wasn't in the plane when it crashed. The other thing that happened is within a year of getting my pilot's license, my flight instructor flew into a tornado off the coast of San Diego called a waterspout. And she talked to air traffic control on the way down and explained what was happening. So anyway, it motivated me to study aviation safety very seriously when I went back to school. So that's my long story. This is Jeremy Castagno. He's going to be doing the second half of the presentation. He's a PhD student at the University of Michigan. Formerly, his connection to safety was being a control systems engineer at Valero Energy, where a lot of things can go wrong if you don't keep the equipment going well.
That is true.
So we're both in the Robotics Institute at the University of Michigan, which is happily undergoing expansion. We're going to be in a new building in the next year. So that's it for us.
Thank you.
You'll be back later. So Jeremy stood there a long time and had to listen to me ramble on. One of the things that's a problem with me being a pilot is I like to ramble on with stories, but I'm not as bad as the old guys who tell stories for longer. None of you raised your hands, so I think I'm not insulting anyone. So this is an air sim with Unreal Engine graphic to illustrate what it might be like for a drone that's flying over a busy urban area to have a problem and have the software say, hey, time for the contingency management to kick in, you need to land. Where are you going to go? Well, in this case, we didn't simulate a lot of cars, but imagine that the street is flooded with rush hour traffic and there are pedestrians everywhere. So the drone is going along, and it needs to select a landing site. Rather than do any sort of aggressive diving maneuvers, it decides to basically continue going forward, sees a big flat area in this building, and now it's going to approach and land there. Now, one of the things Jeremy will tell you a little more about later that was kind of fascinating, a lot more people are getting into using things like Unreal Engine with simulators to give yourself a realistic graphics environment. One of the things that Jeremy found as he was doing this research is that there's a lot of detail if you look from the perspective of the street, but the rooftops are not all that well done yet. So maybe you'll be hearing that he's provided a lot of upgrades to the rooftops in Unreal Engine over the next little while. If you guys do it, please let us know. We'd like your rooftops as well. All right, so let's wind all the way back. If you look at where aviation began, it really began with tin cans with wings or whatever fabric, cylinders with wings, whatever you want to call it. So aviation itself evolved from a time before there was even instrumentation, where you had to look out the window and fly and there was nothing else, to a time when there were radios, and those radios may give you beacons, but they weren't precise. You couldn't follow a blip on a moving map display. You had to triangulate between beacons. And the human was the data integrator, no computers. To now a time where there are flight management systems on the tin cans with wings, like you see the 787 in the middle there, and then a whole host of unmanned aircraft. The unmanned aircraft, like the one on the bottom right, tend to have a room full of people controlling them. So when contingencies need to be handled, maybe some are locally handled on board, but my understanding, things like emergency landing, if you have, say, a mission to go across the country or world, there's a team of engineers that plan in advance, and it's a pretty significant cost to do that. So if you're just carrying a package the last mile, you don't want a team of people planning your contingencies for you. You want software to do that, because you're not going to drive down cost very much if you have a lot of people doing that. So what that means is that you need to take the software and the human oversight that had been in the cockpit of the manned aircraft and in the trailer of people supervising a very high-cost unmanned aircraft and condense it into a form that you can put on a fairly low-cost, modest-power computer on board a drone. So drones come in many shapes and sizes, and we've seen some exciting ones here. The basic classes are fixed-wing, Multicopter or rotary wing, that includes the helicopter with a big disc, or the multicopters that have 4, 6, 8, however many blades on them. And then the emerging eVTOL, electric vertical takeoff and landing, which is what Amazon showed yesterday at the keynote, which allows you to convert between horizontal flight, which could be pretty fast, where you're using the aerodynamics of lift to give you a lot more efficiency so that your batteries don't deplete as quickly. But you're also getting the ability of using the multiple motors to give you not only a transition to vertical flight, which allows you to take off and land on a very small, perhaps unprepared spot, but also allows you to have good maneuverability and reasonable payload capacity. So you want all of these things. Nothing ever comes for free, and the designs haven't really stabilized yet. So everybody now that does passenger transport either builds a big blended wing body, which is a flying wing, or a tin can with wings, and we're pretty good at that. We see a whole lot of different designs. There's still a lot of multidisciplinary design optimization, where if you ask aerospace, they would say it's aerodynamics, propulsion, and structure. And I would say that you have to add to that avionics, software, and instrumentation. But that whole problem is pretty challenging. Now, say that that's done, and you have a vehicle, and maybe it even has some redundancy and resiliency. Right? If you're flying over people, you probably don't want one failed sensor to make the thing go crazy and go into a crowd. Right? So that's something, even though we don't have regulations in place to require small vehicles to have redundancy and resiliency, we will move that direction, because no one really wants a system that's going to hurt people in cities. So now we step back and say, well, how do you give the best situational awareness possible to this vehicle, whatever size it is? And the answer is you take the data, which is comprehensive, that we have access to. At a university, most all that we have is open source data, but there's a lot of it, as you guys all well know. Geographic information systems, lots of city data that tells you where the buildings are, where the lots are, what zonings you have, OpenStreetMaps. I'm going to show you a chart with all that stuff later. But what you really want to do is to take that data before you ever fly, just like a well-prepared pilot would plan their flight and have charts ready to go, instrument, visual, whatever it is that they needed for that flight. The unmanned aircraft or the urban air mobility platform is going to be best prepared for the flight if all of the data between their origin and their destination has been stored in a compact form, easy to access, small footprint, to be used to manage contingencies in real time. Sorry about the small print. It seemed good when I was looking on my screen. So then what you want to do is to have the small UAS in this picture use all of the sensors on board. And you heard Amazon yesterday say, I think they were using video, thermal, and ultrasonic sensors to sense their environment, and then you would supplement that with inertial navigation systems, which would give you GPS and attitude information for on board. That gives the vehicle the ability to sense its own state and the state of its environment. And then you supplement that with map data. The map data is going to tell you where obstacles are in the environment, like buildings, power lines, et cetera. It's going to tell you where roads are, where waterways are, where airport runways are, where vertiports are, the list goes on and on. All of that information can be parsed and processed and stored in data structures that can be pulled in real time. This picture also is acknowledging that in the future, we're not going to have line of sight flight where someone with a transmitter is looking up. We're not just going to have really expensive satellite-based communication. We're going to have some combination. Some vehicles already have this, right? So maybe you have 4G going to 5G, you have Wi-Fi, and then you have satellite as a backup. Right? This is desirable. It gives you the kind of redundancy and resiliency that you would need. If one failed, you go to another. So that means that in real time, you not only have access to pre-stored cache data of static information like buildings, because they don't move between flights, but you also have access to other data that might arrive in real time, like traffic and population data that we'll be talking about later. There's an operator in this picture. We'll see how that goes. Right, so then you want to take the stored data, fuse it, and use it. Now, I'm an academic, and so you can't escape a presentation without at least a couple of citations to the literature. Our group is not the first to ever think about taking non-traditional information and use it for contingency management in flight. A lot of the work originally started out thinking about manned aircraft, large commercial transport, and it has more recently evolved to be thinking about the small unmanned aircraft operating in urban centers. So what kind of sources of data might you want to find? Man-made structures, the slope of terrain, weather information. Right? If there's bad weather, one of the first decisions that a plane or a pilot would make is, do I fly? And if there's a cell of bad weather, if you're already flying, then there's a question of how do I go around it? But the first step is to know about that data. Now, one of the things that you find is weather radar is pretty expensive, so it's not clear that a final mile delivery drone is going to carry anything like that. It instead would be networked to get that information from the cloud or from an operator, depending on how it was getting it. You also want to have other information that gives you more about the risk to people and property. Right? As we move from manned to unmanned aviation, the risk shifts from save the airplane and save the people on board to who cares about the airplane? Now, maybe we care, but it's less important to save the airplane than it is to make sure that that airplane never brings damage or harm to people on the ground or expensive property on the ground, with the people ranked highest. So what that means is if we know where the people are and we know where the traffic or manned vehicles are, then we know what we shouldn't fly over. And that's not because FAA has said this is a no-fly zone. It's because it doesn't make sense to fly over Times Square on New Year's Eve, even if it was legal, because you're bringing the maximum risk to a lot of people that you possibly could. All right, so this is that chart that shows the data flow from raw data to where we get to the point that we can analyze risk and use it in contingency management for small unmanned aircraft. So the raw data largely comes from GIS, Geographic Information System, which has a combination of LiDAR data from overflying aircraft, different resolutions in different cities and around the world, but still largely available point clouds of the buildings and the terrain. And also vision-based data, video data, image data from satellites and other sources. So if you take that and you process it in advance, then what you can get is a map of features in buildings. And in our case, we're emphasizing rooftops and specifically finding flat, clear areas on rooftops to supplement others. So then you add to that census data and cell data, which you can fuse together to get the best possible occupancy grid for that area, and terrain data, so that you end up processing it and abstracting it to give you information on buildings, landing sites, population, and terrain. That's used in two ways in contingency management, specifically for emergency landing planning. One is, how do you minimize the risk of the area that you're flying over? And the other is, how do you choose a landing site that minimizes risk? So the first thing I'm going to talk about, and again, this is more background, no rooftops, is what happens when you need to urgently land or have an emergency landing in open areas. So you're not necessarily choosing the rooftop. It would be a bad plan for a fixed-wing airplane that had a pretty significant stall speed to land on a rooftop, right? So it doesn't work for everything. So let's start with the vehicles that can't land on rooftops, and then we'll move to the vehicles that can. So in contingency planning itself, what we want to do is to give maximal situational awareness with the data sources I just mentioned to the software on board that may have to build this plan in under a few seconds. Now you may think, well, why do you need it so quickly? Well, if you're flying at relatively high altitude, you don't. You have time. You can think about options, maybe even negotiate with people, pilots or ground operators, on what you should do. But if you're a low-flying drone or an urban air mobility platform or even a Cessna on approach to an airport, then it could be the case that you can't remain up for more than a couple minutes. And if you don't turn your nose in the right direction in a few seconds, you might not make it to a safe site. So that's what this process is about. So this chart with ugly yellow and white print, maybe it's maize, right? Maize and blue for Michigan. I don't know. This chart is about, I don't know, at this point, 18 years old. This is a common sense pilot's view of what do you do in an emergency landing. Well, the first step, which you may not be able to read, says calculate the footprint. So the footprint, which has been done for decades in aviation and even landing the space shuttle, for example, is to draw an imaginary geometric figure like a circle on the ground and say, this is where your plane can go. Now what? Where do you want to choose in that footprint to land? So once you have that boundary, then you can choose landing sites. This diagram is looking at runways, which are what you want first, and then it's ranking them based on length, width, wind conditions, and so on, and then building a plan to that. So everybody always asks about the Sully case. So what happened here? Well, obviously he landed in the Hudson River. There was a movie. He was a great pilot. One of the things that he said in his testimony was that he did not have an automation aid that told him that he could make it back to LaGuardia. If he had had this aid, he might have done it, because it was not a safe decision to land in the river. Right? There are so many things that could have gone wrong. Fortunately, everyone lived. This plot is the flight path that was actually flown. And let me recommend to you, if you have free time on the weekend, go to the NTSB accident docket website. If you search for that on your favorite search engine, you can find it. And these days, you can download the black box data, which is in a CSV format, and plot it just like that in a couple of minutes. So it's a great, I don't know, hobby? Maybe for me. Well, anyway, so you can take this data, and one of the things that we do when we're looking at what-if case studies is we plug in our software at any point in this flight. So here, there's a little square near the top, which happened right after the geese flew into the engines, and we plugged in our flight planner that had predated this actual flight by about 8 years, and we said, what if our software had been in place? So this is the what if. It would have returned 3 possible flight plans, all 3 of them going to different runways at LaGuardia. And this turned out to be a pretty fascinating study, because what you find is that if you immediately begin the turn back, that you have your choice of 3 runways. And all that was being used here was a geometric flight planner. There was no machine learning. There was no computationally complex search. It was all about turning and going using simple geometry. So this is something that could be certified, and should be available on every aircraft today, yet it's not. They're not rooftops, but this is for all of the others, the fixed wing. So in this case, if this automation aid had been available, we probably would not have even heard about this plane, because it would have gone back and landed. And by the way, this was with a safety margin, because the way to do this is not to use best glide, which is the shallowest possible angle. The best solution is to use halfway between best glide and steepest descent, which gives you margin. So this was not close. This could have been done. If you wait more than 12 seconds to turn back, then you can't reach the runway anymore. So in this case, that motivated 2 things. 1, the automation aid, and 2, data link-based air traffic control. Because if you listen, in this case, to the air traffic control transcript, you find that it took more than 12 seconds for Sully to make the air traffic controllers understand that he had double engine failure and needed to come back. So they have to come together. All of what we would talk about then in the grand scheme of coordinating traffic for contingency management for split-second action necessitates getting away from voice-based air traffic control and moving to secure data link. All right, so in a very general sense, if you have a failure or another contingency, let's say you just want to get out of the way when an emergency vehicle like a survival flight comes through, you need to land. Something has happened. You have 2 possibilities. One is that you're in an area where when you scan with your onboard sensors, which is where the majority of the research has been, you find a spot and you go there. If you can find that, great. What we talk about today doesn't matter that much, right? Because that is just the simplistic sensors, hey, there's a clear field, I'm going to go there, done. If, on the other hand, your sensors cannot immediately find a safe place to land, which would be likely in that urban environment that I showed you earlier, you need to look beyond the range of the sensors. So all of this data, all of this wonderful set of data products that we have access to today can come to bear to give the machine far more situational awareness than a pilot could ever have, because it is not hard to store the geometry of empty fields and flat rooftops, among other things. So that's really where we're focused, is a map-based planner that activates when you need data that goes beyond the range of the sensors that you carry on board your vehicle. So then you build your plan and you execute it, and then you see a loop. When you get to where you want to go, let's say it's a flat rooftop. Well, the rooftop hasn't changed, it's still flat, but maybe there's a roof deck party. Well, that was a bad choice. As you approach that roof deck, the last thing you want to do is to land in the middle of that crowd. So you still have to continue. We're not saying that this is 100%, right? If you have static data, you do the best you can. Pilots do the same thing. And when you turn around and execute that plan, you have to act again with your maps if you still can't find a safe place to go. Now, ultimately, you could raise your hand and say, hey, if I loop long enough, whatever bad thing was going to happen is actually going to happen, right? Well, yes, and that's life. But you've given your machine the best shot. So this is an example of not rooftops, but a road-based data set that's used for emergency landing. So you see on the bottom right, asymmetric straight lines. For fixed-wing aircraft, roads can be a good choice of landing site. Now, ideally, there won't be traffic on them, right? But there have been many cases every year, especially in areas like away from Las Vegas, but in the desert. If you have a problem, that is your choice. You always land on a straight, flat road, like Interstate 15. Well, this is showing an area of New York, right? So with OpenStreetMaps, which is an open database that we were using just for this analysis, you can take away power lines, overpasses, curvy road segments, and you're left with this type of map. The asymmetry is because you want to go in the direction of the flow of traffic. If you also have traffic data so that you know the flow speed, like you get on your app on your phone that tells you that it's green traffic and you know the speed limits, then the idea here is if you're a fixed-wing airplane, you need to have a speed that's greater than stall. So ideally, what you want to do is treat that road as an entrance ramp from the sky, right? And then when you come into the traffic, as long as there's a gap, you don't have to even hit anything, even if it's busy. So I don't have the picture shown here, but there are some motivating examples of that where the crew, the pilot, has gotten lucky. The automation doesn't have to be lucky because it has access to data that can help it find where the gaps are. This is an example of a heat map of population. This is in Milan, Italy. The reason we used that is that there was a competition data set of call detail reports that was available to use. So what you see here is how the population changes as the day goes by. On the left, you see early morning before the business day is started, and you see a flight plan that goes from somewhere near the south of the city center and chooses a low-risk, lightly colored landing site that's just outside the city center. After the day has gotten going and you see the high density of population downtown, the vehicle decides that it's higher risk to go across that area and lands out of town. So this is just showing how the flight plan can be impacted by this updated data. In this case, and I think there's a citation at the bottom, what we were proposing is that you use the census data more at night when people aren't using their phones, and you use the call detail report style data during the day, and you basically fuse them. One of the things that was fascinating about this data set is that, of course, you can watch people go into special events. There was a World Cup soccer game during the time that we had data. We could watch the people go in, see the density become really high, but then everybody disappeared. Because during the exciting segments of the soccer match, no one was using their phone. So it actually calls into question how you're going to use this data, right? You actually have to process and watch the people move. You can't just look at instantaneous snapshots and say that's it. So anyway, this is a snapshot of the non-rooftop data sets. And so now I'm going to walk off the stage and let Jeremy, who's the main PhD student that's been working on the rooftop landing research.
Thank you,
30
Ella.
minutes and 20 seconds.
She's a really great advisor. It's amazing every time she gives a talk. I learn so much about aviation. My background is actually in chemical engineering, so there's so much I can learn just from Ella, just when she talks. Anella invited me to work for a PhD. She told me that she wanted me to focus and bring in autonomy and safety for UAS in the skies. She asked me to specifically look at how to handle that when you're in urban cities. And so what I'd like to do is kind of show you a very brief kind of simulation that kind of shows some of the obstacles and challenges that a UAS might face if it was operating in a city. And so what you're seeing here is a UAS. You're seeing a simulated city. The blue boxes represent buildings. You're seeing a UAS carrying out some sort of mission. But of course, some type of urgent situation occurs. It needs to land, and it uses its local sensors, like we talked about, to try to scan around itself, whether it be LiDAR, vision, sonar, whatever it is. But unfortunately, you're in a busy city. There are sidewalks that are full, and there's streets that are completely full, and there's no place for you to land. And so what you might want to do is to have this onboard database that's onboard this UAS that broadens the vision and understanding of its awareness of its surroundings. And now it can see and understand so much more about its environment. It sees the parks, it sees the open areas and brownfields and so forth. But in addition to that, what I was focusing and I've really started working on is also buildings. Specifically, all those blue buildings are actual flat roofed buildings that have excellent topology that's needed to land on them. And so this talk is going to be talking about bringing flat roof buildings as a possibility for landing sites for UAS. Now, that was just a simulated example, but let's look at some actual satellite images of what these roofs look like in cities. So we have 3 different cities here. We have Manhattan, New York, Ann Arbor, Michigan, and Witten, Germany. And what you're seeing here is that if a UAS were operating here, you'll see they might find some difficulties finding these nice, big, brown, open fields that people want to land on. In fact, I really don't see many there at all. But what you do see, what I did point out, because I love them, are these big, nice, flat rooftops, which are very accessible to be landed on. And in case of emergency, what we are postulating is this is much safer than landing in a sidewalk. So that's great, but let's be very clear about what information we need about flat rooftops. So we need to know, first of all, where all the buildings are in our cities. We need to know their outlines and so forth. So we also want to know their 2D shape outlines. A piece of point information is just not enough. We want to know the shape of the actual landing site that we might land in. In addition, we want to know the building height, so whether we have to climb or descend. In addition, we want to know the roof shape of the building, whether it's a flat roof building or whether it's not even flat, it might be like gabled, has a peak roof. So where can we get all of this data? Is there some database that exists somewhere that has all this rich information for us? Well, the first place I started looking 2.5 years ago was like map data. And so you've probably all used Google Street Maps or OpenStreetMaps or whatever. If you zoom in far enough, you can actually see the makeup of actual building roof shapes. And that would be a great piece of information to tell you. So OpenStreetMaps is an open source geospatial database that has incredible amount of information. It's all volunteer-based effort, and they have really good building outlines in a lot of places in America and all across the world. They have also some limited information on building height, so there's a database that can have that. And they also have very limited information on building roof shape. So very often they do not know if it's a flat roof or a gabled roof. However, there's other data sources. There's also public city data sources. There's 2 great ones that I found. SandGIS is probably one of the best ones I've ever seen. It's made by the government, it's funded by the government, from the city government of San Diego, and has incredible information about building information, land use area, and so forth. And there's also New York City Open Data. However, none of those databases have any information about building roof shape. But maybe we can look at different data sources. So we have airborne LiDAR point cloud data. On the picture on the right, you see Manhattan, New York. And this is just a visual representation of what it would look like if you just pointed the point cloud and color-coded by height. You can look at that data, and I'm sure many of you can, not just me, but make out some flat rooftops that you can see in that data set. So maybe we can somehow use some of that information as well to extract flat roof information. The United States Geological Survey releases all of this data source. It's all open source and available. And many other countries do as well, such as United Kingdom, Germany, and many others. Many people often say that this data is quite limited, but if you look at that graph on the bottom left, I would definitely say it doesn't make up all of America, but it makes up quite a chunk of the available data that's there. It's quite comprehensive, and my opinion is it's only going to keep getting better and better and better as we become more data-centric focused, and we're very open in sharing it. In addition to that, there's satellite images. Here's a picture of Ann Arbor, Michigan. This picture really doesn't do it justice, but you can actually continue to zoom in and zoom in and zoom in and zoom in until you get right in front of a building rooftop, and you can see very crisp and clear what that rooftop looks like. And so satellite images are also released by USGS. They're very high resolution, 10 to 30 centimeters per pixel. They're all geo-referenced. All these data sets are geo-referenced. We understand where every data point is located on the surface of the Earth, so we can somehow merge and do multimodal data fusion with them as well. And this is also available in many different countries. And so this next part I'm going to talk about is how we can use all this information together to create a machine learning model to learn and predict roof shapes. And I'm definitely not the first one to do this. This is just a method that I decided to try out and use, and it's been pretty decently successful. So here's just a basic overview diagram of how this process works. Starting on the left on this diagram, we take our raw data sources, this LiDAR information I talked about, building outline information, satellite information. We fuse it together and we pre-process it, and we can generate two different images. One being a LiDAR depth image, and then the other one being like an RGB image, like a satellite image that's been cropped up of the image of the building that we know we're looking at inspecting. We can take this piece of information and we can send them independently to two convolutional neural networks that extract really good high-level features that describe features that are important for identifying roof shapes that we've trained. After we've done that, we can even send it to a random forest classifier that can take these much reduced dimensional information to classify and predict a roof shape. And so I'm going to talk about a little bit about how this kind of process works and some of the success of it and some of the not so success of it. So first, in order to do this process, we need a labeled training data set to do this. We're using supervised learning. However, when I started looking at this around 2.5 years ago, when I just started my PhD, there really wasn't anything out there. It was a little bit frustrating, because I didn't want to spend my time labeling data, but that's exactly what I had to do. I looked at 3 different cities. I looked at Manhattan, New York, Witten, Germany, and Ann Arbor, Michigan. 3 completely different cities, different architectures, different everything. And I produced a manually labeled over about 10,000 images. And what you're seeing here are some of those images yourself. You're seeing some skillion roofs, which is a flat roof that's been angled that has some relief to it. You have your classic flat roof that's completely homogeneous in color, what you can see for the LiDAR depth image. And then gabled is like that residential where you see that, when you look at the depth image, you can see that white peak going down the center representing this higher elevation. And so forth, we generated basically all these images and labeled them. And we labeled them. For the very first time, the reason what kind of drove me to try this is I had actually just taken a machine learning class, just taken one, had learned it, and I was like, I want to try machine learning to try and do this information. And I wasn't super confident in my abilities, so the very first time I wanted to try something dead simple, just see if it would work. And so I looked at one city and one city only. I looked at just Witten, Germany, and I had about 2,500 buildings that were labeled and I worked with. And these buildings all had pretty similar architectures. What I mean by that is that a flat building looked like any other flat building, and a gabled roof building looked like other gabled buildings that were there. So it wasn't incredibly challenging. That's what I'm trying to express. I also, when you do this automatic pre-processing and generating these images, some of them come out very malformed. And what I mean by that is that sometimes there's like a occlusion or shadows that are cast on the satellite images. A human couldn't even make out what the roof shape is. Or sometimes there's trees overhanging a rooftop, and then the point clouds would hit the trees, and then you can't even see what the roof shape is. So I actually had to manually remove about 40% of the data for this very first test. And then what I did is I split this into a training, a validation, and some test sets. And these were kind of the results that I got. So if you were just looking at satellite images, you got around an 86% accuracy. With the LiDAR image, you got around 97%. And with the combined, it was around 98%, so a little bit more accuracy. So the conclusions were that if you had really, really clean data, you can get really excellent results. And by combining modalities, we are able to increase accuracies and predictions. But was this realistic? No, it wasn't realistic at all. A human, me, had to manually remove all these images to achieve such a high accuracy. The model and the automated prediction system shouldn't really require a human to step in the loop and say, this is bad data, don't make a prediction. There's no way you can use this data to make a good prediction. The model was also trained in only one city, so we didn't really see how well it could generalize across different places. And the most important thing that I kind of got from working with this is that it's really important not to put bad data in our database. What that means basically is that if our model says that something is a flat roof, it really needs to be a flat roof. I don't want to land on something that's really not a flat roof. And if I see bad data, we need a way to kind of label this as an unknown prediction. And so to add more realism, I added this kind of new class that I call this unknown class, and I lumped and put all these malformed images in there. And in addition to that, any times I saw architecture, because now I was in different cities, Manhattan and Ann Arbor and stuff, that didn't really fit into the little 7 categories I liked, they also went into this unknown class. And so you can kind of see some of this, the bad images, like on the top left here, there's clearly no building there whatsoever. And you can see some very malformed images in the lighter images. Maybe there was occlusion from trees or whatsoever. So basically by adding that, I was able to create a new class. And what I did first is I made one data set that combined Manhattan and Witten information, which are very totally different architecturally different data cities. And I made a training, a validation, and a test set on that data set. And then I made a completely independent second test set, which was from Ann Arbor, so completely independent. And so this first one is just to kind of highlight some of the work, how I did the training for the CNNs. We used the technique called transfer learning, which I think Andrew Ying was talking about today. And basically, we tried out many different architectures, ResNet 50, Inception v3, Inception ResNet. And I tried out many of them to try to see which ones were the best ones to extracting features for predicting roof shapes. For RGB images, for satellite images, the best one that performed the best was actually the largest network, which was the one I trained with, was Inception ResNet. It did the very best at extracting the most important features that could be used for classification. What was interesting that was on the lighter image, which was the most simple image, just a grayscale image, the one that did the best was actually ResNet with the smallest and simplest of the networks. So in the end, what we had one neural network that extracted features for satellite images, and we had one more neural network that extracted images from the depth images. So now what we did is we used those extracted features, we trained our random forest classifiers to use them to make predictions, and these are some of the results that we got. So first things first, you can notice that accuracy drastically dropped. It went from like 98% to much, much lower. So for the test set, for one, which was the Manhattan-Witten data set, it was around 73% accuracy when you were looking at satellite images. At lighter information, if you just use that, it was around 84.5. By combining the modalities, we had around 87.5% accuracy. And then our independent test set 2, which was a completely independent test set, never trained, validated, never even saw it, complete architectures 2, completely different city, it got around 86.5% accuracy. So it kind of shows that it decently generalized well across different architectures and different places. But I was still disappointed in some of the results of the accuracies. But one thing that I talked about was that I really wanted to make sure we didn't have any false positives. So I wanted to make sure we had really high precision. The output of our neural networks are these probability distributions. Confidence is what we think are actually the predictions. And we can use a technique called confidence thresholding, where we basically say you have to be 60% positive or sure to make a prediction. And if you're not, then it goes to the unknown label because you're not sure what it is. And by doing that, we were able to increase our precision up to around 95%. I think it was like 97% actually, and our recall was still greater than 70%. So I still think that was still a success in the sense because before, this was the landing spot that you could land in Manhattan, New York. There's just that classic place. Now, these is your landing spots. These are all the different places that there are possible landing spots that have flat-like roof characteristics that you could land on. Now, probably maybe 4% of these are not really correctly flat rooftops, and we probably missed around 25 to 30% of the buildings, but it's still better than what I thought we had before. And that's what I kind of work with. So now that we have this predictions, we have a model that can kind of give us what roof shapes look like, how do we build a map with it? And so Ella already kind of showed this picture to you. The basic idea is we take all this LiDAR information, OpenStreetMap census data, everything. We pre-process it. This is all an automatic pipeline. You just move from city to city. And then what happens is we generate these 2 very important databases. And I want to talk about them for a little bit. The first database is this risk-evaluated landing site database. This database has information about all the available landing sites, and it has already been risk evaluated for you before you even take off. And the last one is a map that you can use to do path planning in. So it's like a 3D voxel map that has information about obstacles and all the things that might exist in that region. And another important distinction is now we have the possibility to land on flat rooftops. Those will be a part of our landing site database maps. So in order to create this landing site database, the basic idea is that we have a database now that has information about where all the parks are, where all the buildings are and everything. And then we can use this information, these attributes about this data, and map it to a function that can give us a riskiness value, which we call RL. And this risk value can be decomposed into 3 components. This is often I've seen in literature. We have a terrain cost, a population cost, and a property cost. So terrain cost is the cost that would come to the UAV if it was to land in this area. It's this notion that you would rather land in a very large open brown field than you were to land in a very small shrub. And they're very totally different. You can figure that out way before you even go there. And population cost is like it takes into account census information and so forth, and real-time population, and then also property cost. And so after we do that, this is what a landing site database would look like if you were looking at Witten, Germany. So you can see in the center Luther Park, and it's been highlighted yellow, and the yellow means it has like a lower landing site risk. And ones that are like a darker orange and red, those have a much higher landing site risk. And you can see here also that there are buildings now that are possible landing sites as well, flat-like roof buildings that have the properties that are desired. And so this is what a landing site risk database could look like. It would be embedded, it would be geospatially aware, and it can be very quickly found and queried online in real time by the UAS. So for our cost map database, something that we can do to do some basic path planning to understand how difficult it would be to reach a landing site, we can create these kind of basically like it's a 3D voxel map that also has riskiness inside of it. And so what you're seeing here, the orange represents obstacles. This is of Manhattan, New York, by the way. And the building, that could be buildings, that could be terrain and so forth. And this white and blue, these are those potential fields that can be around buildings. So that would help inform the planner to try to stay away from them. So this is Manhattan. This is a huge map. It's about 1.5 kilometers by 3 kilometers, 130 meters, 2-meter resolution for these grid cells, and it's about a 65 megabyte file, which can be easily put on board, and it can be used in path planning if needed to be. And there's definitely lots of improvement that can be done for compressions, whether using octrees and so forth. But so now that we have these two landing site databases, let's talk really briefly about how we're going to use them. And so what you're seeing here is a graph it's often called the Pareto frontier, what you're seeing here. And it's basically you're displaying two different objectives. You're seeing one objective on the x-axis, which is our landing site risk, and on the y-axis is our path risk. And each of those purple dots are actual landing sites during an emergency situation. And what you want to do is you want to choose the landing site that's in the very farthest bottom left corner. However, you don't get to choose them. That's just the natural, this is what's actually out there in the world. And the green line represents the points that are on the Pareto frontier, which are non-dominated by any other points, which basically means any of those points are optimal points. However, you can only go to one of those points. You can't fly to 3 places at once. And so you have to make a choice. And in order to do that, you need a way to relate the two different objectives with each other. And so we do that by making a new metric we call total risk, which is basically just a weighted sum of the two different risks so you can make a choice about how you want to trade off between landing site risk and path risk. Yeah, and so for this situation, if you chose like an alpha of 0.5 or both objectives are weighted equally, it would probably choose the landing site that's right in the middle, right there with the green line. It would choose the one right in the middle. So how would that literally look like in an emergency situation? So if we were in Witten, Germany, which is what this example is showing, if there was an emergency right there in the center represented, that blue marker represents the site of the emergency for the UAS, and all those colored landing sites, those are all the available possible landing sites that the UAS could go to in this situation. What you're seeing here is the blue circle markers, which are on the top left that are ranked. Those have the lowest landing site risk. Those are parks, those are open areas, low population areas, and so forth. However, you'll notice that they're very, very far away from the UAS. These red circle markers, those are ones that are chosen by our emergency planner that takes into account both landing site risk and the path risk to get to them. And you'll notice it's making a choice. It's totally different than the blue ones. It chooses the ones that are closer by near parks, rooftops, and so forth. So the planner decides to go to a nearer, riskier park instead of then going to a much farther, larger park. And it's able to make these decisions very rapidly, very quickly. Not just the choice of which landing sites to go to, but also the path planning to give us a really rudimentary path of how to get to the area we need to go to. So I talked a lot about planning and maps and so forth. This final thing is about you've made a choice to land on a rooftop. How are you going to actually do it? How are you actually going to do the choice of where to land on the rooftop, that final touchdown? And so what I wanted to do is I wanted to experiment with some algorithms, some computer vision algorithms, and some LiDAR point processing algorithms, and I wanted to do it in simulation to test off first. So I wanted a really good high-fidelity graphics simulation engine to kind of run some of these works, and I wanted drone physics and sensor models and so forth, and I wanted hardware-in-the-loop testing so I could actually run embedded processors in the loop in the simulation environment. And a really great simulator that does that is called the Unreal Engine. And there's a plugin called AirSim made by Microsoft that brings you those, the drone physics and the sensor models and so forth. And so what I did is I purchased city and rooftop assets, so I had to purchase them myself, and I helped recreate these cities. In addition to that, what I did is I actually physically looked, I looked at hundreds of different satellite images, and I would literally count what things are on building rooftops. There's water towers, okay, that's one. There's two ACs, okay, that's two ACs. I'd count, oh, there's a skylight, there's a rooftop entrance. And I looked at hundreds of these satellite images, and I made up a distribution, basically, mapping of what things are actually on building rooftops that you would find. And I was specifically looking at Manhattan. And from that, in building from those distributions, I was able to automatically generate like dozens and hundreds of worlds that would follow the distributions randomly that generated from what I saw in the real world. And so I was able to generate lots of different worlds with the distributions of rooftop assets that I saw. And so here's just an example of what that Unreal environment would look like. So what you're seeing here is just a city that I built. So the things that I changed were mostly just the things on the rooftops. I made some changes to the buildings, but not significantly. You're seeing water towers, you're seeing air vents, you're seeing rooftop entrances and small buildings that exist on them. The Unreal Engine, you can see lens flare, you can see reflection and so forth that the Unreal Engine can provide for you that kind of shows you kind of realistic textures and so forth. And all of this, I made this pipeline that can all be automatically generated. New cities, new textures, new things. And what you're seeing here is the AirSim drone. It's coming, it has the drone physics. You're seeing a downward facing camera on the bottom right. In addition, there's a LiDAR sensor that we have on this thing, and you're gonna see in a second. And then the LiDAR sensor will be shooting LiDAR rays and as well as camera RGB images capturing the rooftop. And so this next part's going to go really fast, but the basic idea is that we can train a segmentation model that can do pixel segmentation, so we can predict the classes of the items that are in the roof, and we can do a classified point cloud. And this last part talks about how you can create basically a mesh that's on top of this rooftop. We can extract that mesh, and then we can find the largest inscribed circle that's flat that's within that mesh, and then we can find the landing spot that we want to land in. And so you can see here it's executing a trajectory to go to that landing spot and then performing that landing. Just to kind of highlight a little bit more about what that looks like. So you have this point cloud that's been classified on the left. You basically can do like this iterative expansion to the points to try to create this mesh that are spatially connected. And you can honor planarity, making sure that it has a minimum flatness that you want and also minimum distance between points so that you can guarantee there's no obstacles. And then what I do is I can very rapidly transform this mesh into a 2D polygon. And then with that 2D polygon, I can then use a really great algorithm developed by Mapbox called Polylabel that finds the largest inscribed circle in it. And that inscribed circle, that position, is guaranteed to be the optimal, most flat area that's within there that's obstacle-free. And so thank you for letting us talk a little about this. So here's some of our references if you want to look and learn more about some of this work. If you're interested in the data set that I labeled, it's all open source. You can see the data set and look at how all that week's labeling to use. But thank you so much. I appreciate it. I'm going to hand this over to Ella. She's going to talk a little bit more about University of Michigan. Thank you.
Yeah, and he's actually going to stay up here because we'll take questions very soon. So if you've been taking pictures of the other slides, please take a picture of this one because we really like it when you cite our papers. That's something about being in academics. So one of the things that they ask us to do is to shamelessly plug our institutions. So I'm at the University of Michigan. I'm the one who's been wearing the Michigan shirts everywhere I go at this conference. So I'm in two different organizations at Michigan. One is aerospace engineering. Michigan's aerospace program is the oldest program in the country. It had its 100th anniversary in 2014. And it's a pretty traditional department. The subjects are things like aerodynamics and propulsion and structures and dynamics control. But it's slowly evolving over time to get more integration with not only computational science, which is something that connects very well with those disciplines, but also merging where the higher level autonomy is becoming part of what people care about. I also am Associate Director of the Robotics Institute. The Robotics Institute at Michigan is only a couple years old, and the robotics program is now less than 5 years old. We're graduating our first PhD students this year. So it's a very exciting time. In the bottom left, you see that we have a new building. the Robotics Institute building. It's going to be called the Ford Motor Company Robotics Building because they actually are going to be living on the 4th floor. It's the first time this has happened on a college campus, so we're going to be in the first 3 floors, they're in the 4th floor. So you can see there's a lot of different variety in what we do in the Robotics Institute, things from walking and running and self-driving cars, which in Michigan is inevitably big, to the wonderful display that Elliot Rouse and his students had of the prosthetics and how they will help with rehabilitation and other aspects of human health, to the big drone cage that we have, which I will personally advertise because this is like, you know how you always want to work and play at the same time? I get a playground until I retire, right? Which is this 50-foot drone net, which is right next to the robotics building. In fact, it's better than that. It's exactly between the robotics building and the aerospace building. It doesn't get any better. So right now, we've been, this is about, I guess, 1.5 years old. We've gotten a grant to put motion capture in it, and it's going to have eventually edge computing and advanced wireless systems so that it's not just going to be for drones, it's going to be for collaborative robotics projects that walk and drive as well as fly. So that's it. You don't have to clap again. Please ask questions, and thank you for listening.